Good afternoon, everybody. My name is Marek Michalewicz. I'm the director of ICM, Interdisciplinary Center for Mathematical and Computational Modeling, University of Warsaw. We've been running this special series of virtual ICM seminars in computer and communication or computational science since March, late March this year. That is just a follow-up of our Supercomputing Frontiers Europe conference, which turned out to be quite a successful event. Instead of having a stationary event for a few hundred people, we had the virtual event, free to all, with participation of over 1,000 people. So it turns out that promoting science and communicating science and sharing results, COVID is no barrier. We can continue doing this slightly differently. And today I have a great pleasure of welcoming Professor Alan Edelman from MIT, creator of Julia language and many other things in the field of numerical mathematics and parallel computing and many other topics. Professor Edelman is a recipient of last year's Fernbach Award, which is given out at the Supercomputing conference, and we've known each other for at least 5 or more years, and we try to promote and educate people about Julia in our limited way through various workshops at the series of Supercomputing Frontiers conferences, both in Singapore and now in Warsaw. We even run a small project one with Alan on incorporating UNAMs number format in Julia, so that was pretty successful with John Gustafson and the Julia Computing Company. So we have some experiences and we know each other, which is great. Let me just very quickly introduce few of the forthcoming speakers. So I want to whet your appetite and make sure that you know about what's going on. Our next speaker in a week's time will be Professor Sarah Kenderdine, who is absolutely a leader in the world in the field of digital museology. I won't say more, but please follow this up. It will be at least visually and aesthetically very beautiful and very interesting talk. Then in 2 weeks' time, we will have a great pleasure of welcoming Stephen Wolfram, who's the founder and CEO of Wolfram Research, creator of Mathematica. That is going to be very interesting because Professor Wolfram has got new ideas about some overreaching way of describing universe and physical reality. That will be very, very interesting. I encourage you to mark your calendar. Of course, we need to acknowledge our media partners who promote this, help us to reach the audience around the world. That's Datanami, HBC Wire, Enterprise AI, ITWIS, Sztuczna Inteligencja, and Computer World. And if you're interested in checking the previous lectures, there were already 7 lectures in our seminar series. Several of them, all of them were very, very interesting, thought-provoking. We had a couple of talks on interpretation and understanding of COVID epidemic. We had topics on astrophysics, early universe, formation of early universe, and on the HPC in general, and two very, very interesting talks on quantum computing. So please go to our website and see it. Perhaps you'll find something very interesting and entertaining for you. And with this short introduction, let me welcome Professor Alan Edelman to talk about high-performance computing and the power of language. Welcome.
Thank you very much, Marek. It's a great pleasure to be here virtually and address what looks like 120 people and growing by the second. 121. It's kind of fun to watch the numbers continuing to go up. So the title of my talk is High Performance Computing, the Power of Language. And some of you might have actually been at the Supercomputing conference in Denver. That was a sort of half-hour version of this talk, so I'm going to in some sense, a little bit of a repeat, but I get the full hour to be able to expand on that talk. Some of you might have also seen that talk on the web. So again, it's the 1 hour version. And I feel like I should mention in advance that I do have a little corgi who's fast asleep. But if he does wake up, he may bark, and there's very little I can do about that. So just thought I'll give you the warning in advance. Okay, so as Marek mentioned, I work on the Julia programming language. Now let's see, for me to present, I need to have, I see, okay, this is good. Okay, got it. Access to my slides. All right, so the original supercomputing talk was given back on November 21st over in Denver. And by the way, we've made the public chat open at my request. They were willing to do that. I will glance over once in a while and look at the questions. I may not answer them in real time as I'm speaking, but I would like to encourage you to go ahead and communicate on the chat. I guess I've gotten used to the Zoom meetings where people kind of chat away, and I kind of like watching that flow by. So I don't feel like we will have a question and answer session at the end, but at least for this talk, you can also type it here and now, so that's fine. So. Okay, yes, I think the slides will be put online as well. And the lecture is definitely getting recorded. Okay, so the power of language. So let me start by telling you that I've been involved with supercomputing for a long, long time now. When I was a graduate student, I used to earn a little money on the side working on a machine called the Connection Machine at a company called Thinking Machines. And that was, back then, probably the most exciting supercomputer of the day. It's still, I would say, it still wins the beauty contest of the best looking supercomputer. If you've ever looked at the CM2, it was this big hypercube thing that was just very colorful with red dots. And so I've been working on supercomputing back since that time. And what I've been interested in is not how do you get something on a supercomputer, not even necessarily how to make it fast, though of course that's a piece of the puzzle, but I'm actually very interested in making it easy to do supercomputing. It's still the case that not enough people are using distributed computers or GPUs or whatever else is coming down the line. And that's kind of been my lifelong challenge. So when I talk about the power of language, I think about the power of language for performance. Okay, so that's why we do supercomputing, right? This is the supercomputing series. And so performance, of course, is always one of the key things. Okay, but we also want to talk about the power of language for productivity. So I can share a story I heard from a salesman some years ago at a supercomputing conference. I don't remember who it was anymore, but I was having dinner with a salesman, and he said to me, and I thought it was kind of an eye-opener. He said to me, I don't really care if you get a factor of 100 on 100 processors. All I really care is that you can get a factor of 10 and you can do it by tomorrow. Right, and I thought that was very insightful. It's like, I can buy 200 processors, I could buy 1,000 processors, but if you could, I don't care how many processors you buy, but I need that factor of 10 available for me by tomorrow. I don't want to wait months. Okay, and that is something that we don't see enough in academic supercomputing, but maybe, as the world is changing, this is something we could change as well, that we're interested in quick performance. It doesn't matter whether you utilize the whole machine or not, potentially. So productivity measures that. Okay, but there's the power of language for other things. For example, the power of language for impact, right? And so another key metric for supercomputing is, besides the performance that we always see, is how many users do you have, right? Impact is probably measured best by how many people are using your code, right? So a lot of supercomputing applications have 1 or 2 or 3 users, right? And that's fine, that's great. But if we could start getting more applications where we have thousands and tens of thousands and hundreds of thousands of users, some of them do, but I think we can get more having that kind of impact. So I'd like to talk about the power of language for impact. Okay, and then moving along in my little sequence here, the power of language for abstraction. So, we like to tell people that if you ever copy and paste code and then modify it a little bit, then you've missed the boat, right? If you're ever copying and pasting code and modifying it, then really what you should be doing is going back to the original code and building the bigger abstraction so that not only you can use it again without having to copy and paste, but you can go and modify things and everybody benefits, right? And so language lets you build up these sorts of abstractions, okay? And then this one came a little bit as a surprise, but the power of language for community building. And so we see this, first I saw this at MIT and then around the world, where people from very different areas start working together because they're using a common programming language, a common open source programming language. And so people are always talking about how can people work together. You have to learn other people's jargon and whatnot. What we've found is that language itself is the best way to create community. So the power of language for code reuse is one that I've kind of alluded to when I talked about abstractions. Okay, and I've got two more in my sequence, so let me just go through it. The power of language to engage students. And so we find, for example, that there is a certain traditional way of teaching that works well, but there are other choices. So the traditional way of teaching is you show something on a blackboard. Maybe you show an algorithm. And then what you do for homework is you tell the students to code it up, right? And maybe you even give them a partially coded solution and they can sort of fill in the dots, or maybe you just let them go at it. But what we have found is that the students themselves in our classes really like to be able to sort of figure things out. They like the math and the coding to go together, the algorithm and the coding to, they don't want to just sort of do the algorithm and then and now just implement it. They want to fiddle with the algorithm as they code, see if they can even find a better algorithm. So this sort of back and forth approach, which many of us do naturally, but we don't see it enough in our classrooms, is another true power of language. But that's only possible if your language lets you explore. So for example, a lot of traditional supercomputing, where you're using maybe C and MPI, what we've found is that you're so thankful to get the thing working that you'll never mess with it, right? That's not a great state of affairs. Right? What we really want is the code that's so flexible that you're encouraged to tweak it and make it even better, constantly every day, right? And so that's kind of what we're going for with that. And so here's the last in my sequence, the power of language for supercomputing, for high performance computing. Okay, and so as I said, this is kind of a repeat performance of a slide I gave at supercomputing, and I thought I would take it out because the dates are no longer right. But I thought it was fun enough to do, and so I'll keep it in. So the way I kind of started my talk at supercomputing is, you see, for those of you who know about the SC series, the supercomputing series, you know that it's always the week before the American holiday of Thanksgiving, which is in November. And it's always exactly the week before that Thanksgiving holiday, the American Thanksgiving holiday. And so, that would be on people's minds, or at least, those who are, from or living in the United States. And so I thought I would bring up a kind of a children's social studies project, second grade, elementary school, little kids would have this project where they would talk about Thanksgiving past and present. And, this would be a little exercise where you look at the clothing of the time. The American Thanksgiving, takes place during the time of the Pilgrims, in the 17th century. What was the clothing like then and the clothing like now? Or how did people, communicate then and now, right? Or what kind of games were played? Or how was cooking done, right? And so you have these then and now games. And so I thought I would turn that into, you see, I just added the week before Thanksgiving, past and present. And I would turn it into to kind of a history of the supercomputing conferences and talk about what has changed over the many, many years. And so I'm not even sure anymore, but I think my first supercomputing conference was the 1991 in New York. I mean, actually, I can't remember anymore. And then, of course, the most recent one was the one in Denver back in 2019. And oh, here's a great picture of the CM2. This is the connection machine that I claim wins the beauty contest of all supercomputers of all history. I mean, that's my opinion, that this is the best looking supercomputer ever. This is the connection machine. This is the Cray. Back in 1990, the connection machine and the Cray was really what everybody was talking about. Fast forward about 30 years, and now we talk about machines like here, Summit and Sierra, lots and lots of distributed processors with GPUs and so forth. And back then, the only thing that was ever discussed was performance. That was all anybody ever cared about. How close to a factor of n did you get on n processors? That was sort of the only thing that mattered. That's still a lot of what people talk about. But if I could change the dialogue, and I know other people are as well, impact now needs to be sort of the key metric, not only performance. So if I can somehow update how, other issues, back in those days, users would report results. People would get up on the stage and said, I got a factor of 125 on a 126 processor machine, or 128 processor machine. I've been a good boy or girl, right? And nowadays, people want reproducible science. So if somebody goes and tells me they got this performance on this machine, I should be able to go to that machine, or maybe a similar one, and run the code and get and see it all working, right? That's reproducible science. So nowadays, reproducible science is what has to be done. Just getting performance alone just doesn't quite cut it anymore. Okay, back to my then and now. Nobody really talked about composability. Composability is having two bits of code working together. So I used to kind of, almost as a joke, but it became a very serious exercise in my graduate class. So at MIT, for many years, I taught the graduate class in high performance computing. And one year I cooked up this homework assignment, and it was really very simple. The homework assignment was, part one is get something off the internet and run it in parallel, right? That's it. Just grab something and run it. And that might sound very silly, but it was very, very difficult at the time. It's still very difficult for many students to just be able to run somebody's code. But MIT students, they're serious, they worked hard, and I think almost all of them succeeded in completing that part of the assignment. Then the second part of the assignment was get something else and have them run together. I mean, it could have been anything. It might have been, invert a matrix and then do an FFT, a two-dimensional FFT on that same matrix. Anything, compose those two things. And I think almost every student failed. And it wasn't for lack of trying. It was just that nothing composed at the time. And that was a problem, right? And so everybody wanted performance, nobody cared about composability, and that led to a great deal of trouble. Nowadays, composability is what everybody needs. It's still a hard problem, but it's something that we really can't live without. Okay, and so the next thing on my list is portability. And so people talked about portability. There was kind of like lip service to portability. It was definitely discussed, but I would say that not much really happened. I mean, MPI was created, and that helped a little bit. But now the challenge, and I say it's a challenge because this is something that is not solved, is we want heterogeneous portability. We want people to be able to run on their laptop. We want people to run on GPUs, on distributed machines, maybe distributed machines that have GPUs, maybe even FPGAs, maybe TPUs, the ones from Google. So these are the sorts of things that everybody talks about, but it's a very, very hard problem. And it's time to really address that problem head on. Okay? Back in 1990, MPI was just coming out. PVM, some of you might even remember the old predecessor to MPI, which was PVM. And now MPI is starting to show signs of age. People really don't want to program in MPI anymore. There's a problem because in some sense, that's all there is in a certain way on a distributed computer. But it's getting to be old-ish. And in fact, I have a little story to share, which is that I was at a conference when MPI was first being introduced. I'm pretty sure it was over in Oak Ridge, Tennessee. And I'm sure most of you know the name Jack D'Angara. Jack D'Angara was on the stage, and he was talking about MPI. And at one point, I was just this graduate student, and I was kind of timid, but I raised my hand. I went like this, and I said, I have a question. Is MPI going to be what everybody uses for parallel computing, or is that just for like the low-level library writers? Like higher-level people won't be using MPI, right? And everybody went, right. MPI is just going to be like for a few low-level programmers. Well, look at what happened. Most parallel codes these days, the distributed parallel codes are many of the ones to date are still in MPI. The dream of sort of higher level parallelism is still something that we have to work on. All right, moving along. When I started in this business, I remember a small, younger community. People were very excited about gigaflops and teraflops and then eventually exaflops. These days, students have lots of competing choices as to what they might work on. So, AI has gotten pretty hot, and there's scientific AI, and now COVID-19 applications, and so many things. There's so many things our good students can work on. All right. I would say back in the day, we had a few industrial connections. I remember oil companies and certainly, high-end graphics companies. It's easy to imagine that if we can get HPC out there even further, we could have even more industrial connections. We have a lot more, and I think we could have even more these days. And maybe here's my last point about then and now, and I hope this is an interesting point. Your workflow for success back in the day was to roll up your sleeves and performance engineer. That was kind of the way you did it. You performance engineered, and if you kept rolling up your sleeves enough, you'd be able to get lots and lots of performance. So now what I see as sort of a workflow for success is sort of more about building up, first we have to build up libraries, and then eventually SDKs, and then finally domain-specific languages. And where I want to be, of course, is whoops, I don't want to do that. Sorry. Can I get that back? Let's see. There we go. Can I get back my? There we go. Is the high-level language. That's where I would like to be. Okay. So moving along. So let's talk about language. In part because people don't talk enough about language. Very often I will hear a talk where somebody computed something, and I'll ask what language did they use, or even what machine did they use, and it won't even be said. Or I'll read a paper, and the code's not available, so I can't even see what's done, and that kind of bothers me a little bit. So I'd like to point out that there's historical precedent. So philosophers and mathematicians over the centuries have talked about language. I mean, there's Bertrand Russell, for example, who would talk about how language serves not only how to express thought, but it makes possible what thoughts can be created. So if you have the right language, you could think in the right way. The mathematician Henri Poincaré, I actually saw this quote in a museum in Paris along the Champs-Élysées. There was a mathematical exposition, and I saw this quote of Henri Poincaré. This was a few years ago, who wrote that when language has been well chosen, one is astonished in mathematics what's possible. And so, Poincaré was not satisfied to just solve the problem. It had to be solved, with the right notation and elegantly, so other people could come along and do even more things. Right? That's the same thing as what we're trying to do with computing. The philosopher Wittgenstein talked about the limits of my language mean the limits of my world. And then there's my graduate student, Valentin, who he's always rather tickled pink when I put his picture up among these illustrious mathematicians and philosophers. But he likes to talk about computation as applied psychology, where if you have the right kind of language, you can coax performance out of users. And so that's what we're trying to do. All right, so some of you might ask, well, some of you might even remember that there were attempts to use language in HPC with amounts of success and failures. I mean, here's a paper from 15 years ago, or actually the paper was 15 years ago, but the project started already 18 years ago. There was this project, maybe some of you participated in this. There was this project by DARPA called the High Productivity Computing Systems. And they were focusing on high productivity along with high performance. By the way, maybe I can ask this of the click meeting people. Is there a way that people can actually see my cursor? I'm actually pointing to something, but I realize that you can't see my cursor. I don't know if that's not. I'll look in the chat from the ICM University if it's possible. If
Yes.
not, that's okay.
It should be possible.
But in any event, oh, sorry?
Yes, it should be possible if you click the cursor icon in the bar below, below your presentation.
Oh, if I click, oh, I see. I've got a private pointer. And now
yes, we can see it now.
Oh, that's fantastic. You even see my name. Oh, that's great. Okay, just what I was looking for. Thank you very much. Yeah, I mean, I like to point to things with the cursor. So, yes. So 15 years ago, there was an attempt, and some of you may have used some of these languages. The 3 languages came out of this. There was Chapel, Fortress, and X10. I believe Fortress and X10 are kind of dead now. Chapel's still kind of hanging in there, I believe. So these were the languages, and let me tell you, they had a lot of very good ideas, some of which we look at and even borrow from. But something has happened, and when I was at the Supercomputing conference, again, some of you who may have been there may have seen that the Supercomputing conference was at this big Denver conference center, like the big convention center. It was huge, and I took a picture with my camera. There were these kind of plaques with supercomputing over the years, all the way back, we were in 2019, then 2018, 2017, and you could walk through and see all the accomplishments all the years back. And I looked at these very carefully. I looked at every single one of these. Maybe some of you were there and saw them as well. And I noticed that when it came to accomplishments, there was from 1988 to 2010, right? So fully 13 years, there was a mention of programming languages. So there, MPI and other things came along. Some were experimental, some are still here, some are gone. But except for the year 2005, you see, you could tell that I really looked. Except for the year 2005, for whatever reason, 88 to 2010, there was a mention of programming languages. And then from 2010 to 2019, I'll call that the dark decade, they removed programming languages, maybe because there wasn't much development. I don't know why, but for whatever reason, I'll call that the dark decade. But something seems to have gone wrong. And when I was at the conference, I actually did ask if the whoever is, I don't know if the person responsible for these plaques was in my audience, but could we bring it back now for the next conference? Hopefully, we'll be at a conference next year in person. So, what did we miss 15 years ago? What went wrong? And there's a lot I can say, but I think that it was a bit of, I don't want to say it was a mistake, but a bit premature to expect a parallel language to catch on before a serial language caught on. So none of these languages had a user base that, people were doing what they were doing, they were happy with what they were doing, and they weren't going to start working with some experimental language. So what we did is we figured out that we need to have before people are going to use a good parallel language, we need a good serial language. And so we went ahead and created Julia. So we created Julia. I should mention my co-creators, Jeff Bezanson and Viral Shah and Stefan Karpinski. You'll see a picture of them in a minute. But what's happening right now, and this is already I could add a lot more to the slide. Universities already around the world are teaching Julia. Students are using Julia. Julia is being used in the national labs, right? And so we created this user base, and that's what we think was necessary to be able to sort of win this game. Oh, here's a picture of, there's Jeff, there's Viral, there's Stefan. So we knew that the right user base starts with a serial language, and also we said to ourselves that it's going to take about 10 years to mature this user base. Like, we said to ourselves that we are not going to be an instant success. We know that, right? I mean, I think it took Python a lot longer than 10 years, but of course everything's moving faster these days. So it takes, we said to ourselves, it takes 10 years. People are going to say to us, watch Julia. They're going to say, why should we use Julia? Why should I switch language? And people are going to say to us, MPI and Python and all these other things. And we were like, okay, we expected that. And so really our motto is for any young folks out there who want to be very, very successful is, it's an old saying, but it's still true as ever, that patience is a virtue. Okay, and so I can't say that enough, that planning something for the long haul and sticking with it is absolutely what's needed to solve really, really hard problems. That's just the way it is. And so I put on a little collage of just a few folks that I knew about Julia at National Labs. I mean, there are a whole lot more than this list, but just wanted to mention that there's stuff going on in just so many different kinds of applied physics, some of them is sort of hush hush and secure, some of them out in the open, but there's tons and tons of stuff. There was this, some of you might have seen that a couple of years ago, Julia was actually the first high-level language to join the petaflop club. It was doing a big machine learning problem. May talk about it a little later in this talk, but Julia did that. Here's Jane over in Livermore, who organized our last JuliaCon, which was very successful. Oh, by the way, I can mention that JuliaCon 2020 will be virtual, just like this meeting. And we already have had more people sign up than we normally would have had physically. And so that's very, very exciting. And so maybe I'll show you the link in a little bit, and maybe we can, you might want to join and listen to some of the talks. So let's see here. Oh, and this is probably a little old now. Yeah, this was as of October 2019. We have more people now, but there are lots and lots of metrics. This is old. Gosh, I think it's already doubled since these days. When you have open source, you never really know how many users you have. So you use these certain metrics as proxies. Like, for example, number of Julia downloads, how many were done with via Docker Hub, Julia packages, whatever. But the short answer is it's growing quickly, right? That's the main point. All right, let me go and switch to this demo that I like to do some real computing here. And so I'm going to switch to my screen sharing. Good. All right, I see that worked seamlessly. Before I actually go to that, though, let me do one quick other thing, because I want to talk about JuliaCon 2020. So maybe I could just type that in my browser and see. Here it is, everywhere on Earth. And so it'll be at the end of next month, at the end of July. It was going to be in Lisbon, Portugal, but obviously that's not happening. And so I'd like to encourage you to consider participating in this sort of thing, because it's pretty exciting. It's a very, very young crowd, and I always tell people that if you see a young crowd, then you see the future. I've gone to certain supercomputing conferences where I see a much older crowd, and my doorbell's ringing, but I'm going to ignore it. So yeah, so in a much older crowd, that you just think about how the demographics go. So, can I just excuse myself 1 minute? I terribly apologize, but let me see if I can mute myself for a second. I'll be back in just a second, but yeah. Sorry about that, everybody. This is what happens when you're at home. Okay, where was I? Okay, I was sharing my screen, right? Okay, there we go. All right, good. All right, can everybody hear me? Should be able to hear me. Okay, yes. Good. All right, so let me return, and I'm going to give a demo, just a small little demo. That it's the same demo I gave at Supercomputing, which just gives a little bit of a feel for the dream. And when you give a demo, demos are really very tricky. First of all, giving a live demo is always very tricky, because things can go wrong. But if those of you who actually know me know that I really, really like to give live demos. And when they go wrong, well, if you've ever been involved with computing, things go wrong. I mean, come on. I mean, is that really a surprise? But when things go right, it's pretty convincing. So let me give a feel for the dream. So this is a Jupyter notebook, which is one way of executing Julia. Some of you might be familiar with Jupyter notebooks. In fact, Jupyter itself is, the JU is Julia. You may not know that. The JU is Julia, the PYT is Python, and the R is the R programming language. And so Jupyter was trying to be language agnostic, and so that's what the Jupyter ecosystem is all about. So so I'm a big fan of linear algebra, and I love linear algebra. Some of you in the audience might like linear algebra. Some of you may not like linear algebra. You may not even, or maybe you've never studied it, or maybe you're experts. Either way, if you're an expert at something else, I think you could translate what I'm going to tell you to your own domain. I don't think that's a big deal. But suppose, I'm just going to speak in linear algebra. Suppose you're doing something. Now, there are times when you can call traditional libraries. Some of you may know about LAPACK, which is how most dense linear algebra happens in languages like Python and R. And even Julia calls LAPACK for its for some of its linear algebra, right? And then there was the ScalaPack project, which was the scalable linear algebra package intended for distributed computing. I think that's less widely used, but again, it's a library. Another one for sparse matrices. Maybe some of you know about ARPack. It's the Arnoldi package, and so if you're using a library and the library is working for you on your computer, if it usually these are serial algorithms. Sometimes they're in parallel, multi-threaded maybe. But if you're using these things, all is good. But what happens if you want to innovate? What if you want to go beyond the traditional libraries? You've got a special problem, and you've got something that you want to customize. You've got something that you want to customize, and you want to do something a little bit different, or you want to try out something. How do you do it? Well, these packages make it almost impossible, right? You have to sort of get into the thinking of these systems. In fact, many of these library writers will tell you don't even do it, because leave it to the experts, which it's got some merits, but I'm a big believer in anyone could be an expert. Open it up to the entire world, open source, and you never know where your next expert will come from. So to give you the idea, let me make a matrix where I know more than the libraries know, okay? So here's a picture of a very special kind of matrix. It might come up in an application, or maybe it's just artificial, but it'll give you the idea. I want you to imagine a matrix where you input a vector, right? You input a vector of n parameters. In this case, it's just going to be 3 parameters. And I'm going to create the diagonal of V plus V times V transpose. Okay, and so here, there's only 3 numbers in here, right? V1, V2, and V3 are the only numbers in here. Of course, the matrix, if written out in traditional format, would have 9 entries. But the data structure only depends on 3 entries, right? And in general, the data structure would have n squared entries, but it would only depend on n parameters, right? And sort of the usual thinking would be don't even calculate these n squared entries, right? Just keep the reduced data structure, keep the n parameters. That would be the way to do it. And so here I'll show you how you do it in Julia. What you do is you create a custom type, and I think I've done this already, but that's fine. I'll call it a supercomputing matrix, and there's a little bit of extra punctuation in Julia, but really basically what I'm saying is that one of these matrices will depend on a vector. And what do I have to do to get this thing to work? Well, I only need 2 things. I need the size, and I know how to be able to read an index, right? And so here I'll give you an example. I'm going to create a supercomputing matrix with the 3 numbers 1, 10, and 100, and look, I've created my 3x3 matrix. If you actually plug in 1, 10, and 100 into this kind of formula here, into this matrix, this is what would come out. But what you see here is just for human viewing. It's not exactly what the computer would type. But if we dump the matrix, which is Julia speak to say, what is the data structure, you'll see it's based from 1, 10, and 100. Of course, you can cast it into a matrix. You could dump the matrix of A, and that will actually compute the n squared story. Okay, so I've got a special matrix that LAPACK doesn't know. Okay, and I like eigenvalues. I've got my own little largest eigenvalue solver, and it's a little thing I wrote. It's just a Newton method, if you know what that means. But the point is, it's short, and I wrote it myself. I'm calling it eigmax. Now, Julia has a command called eigmax, which calls LAPACK, but it's going to be overkill for my matrix. But you see, I can type eigmax on my data structure. It uses this algorithm, or I could actually call the LAPACK, and you could see that I get the exact same answer, which is reassuring. Okay, but this algorithm is going to be faster. It's going to be based on what I know. So again, my purpose of this example is not to talk about linear algebra and not to talk about LAPACK. It's talk about building into an ecosystem. I just added to eigmax, right? I didn't call it my eigmax, right? It's not my eigmax, not new eigmax, right? It's just eigmax. I'm adding to the ecosystem, and I could publish this in effect, and other people can call it too if they want to use something of this type. Okay, but what's really interesting is that I can go heterogeneous. So I can create a coup array for CUDA, or I could create a distributed matrix. I'm making it small just for purposes, but in a minute I'm going to go large. And now all of a sudden, I'm running this on a machine that has GPUs and distributed computing, and these matrices now live on the GPU, or they live, in this case, they live in a distributed way, right? And so, of course, I can convert it back. I could cast it back to the front end, and then you can see it working. So the fact that this is a coup array is shown here. The fact that this is a distributed array is shown here. These are just plain old ordinary arrays. By the way, if you're wondering about what all these words mean, maybe I should tell you. 3 by 3 is an array, makes sense. The elements are integers, and it's a two-dimensional array, so it's a matrix, right? If it was a vector, it'd be a one-dimensional array. So let's compare some timings, but let's crank up the numbers. So I'm going to go to 4 million, and I'm going to create a random vector with 4 million random numbers, right? So nothing special about these numbers. Random, normally distributed. I multiply by 0.1. I don't know why. But there's 4 million entries. Here you can see the 1. It's a vector, right? And here's the first bunch of entries, and then dot, 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 and then here's the last bunch of entries. So 4 million entries. And now I'm going to create an SC matrix. Now, remember, it pretends to be 4 million by 4 million, but I don't have a computer that can store that much. I can't store 4 million by 4 million entries. What I can do is only store 4 million, and that's, of course, what's happening, right? I can also do a distributed array, and I'm storing 4 million. And here's the GPU version. I'm storing 4 million. Now, if I were to calculate eigmax using my fast algorithm, I'll run twice to get a good timing, you'll see that on my local machine, it's about half a second. On the distributed machine, and I'm just going to do it in front of you just to show that nothing's happened, I think it's run on 4 processors, not very efficient, I guess. So I'm getting maybe a factor of 2 or 3 speed up, not quite 4 on 4 processors, but that's not bad for doing no work. Notice, I'm just running the same algorithm on a distributed computer, or now I'm going to run it on a GPU. And here it is only 10 milliseconds, right? Or yeah, about 9-10 milliseconds on the GPU. So let me kind of pause and point out that this is an amazing thing to me. I wrote a little eigmax algorithm. It was up here. I'll go back to it. There it is. I wrote a little Newton's method, okay? And I didn't ask myself, how do you write it for GPU, or how did you write it for distributed? I just wrote it, okay? And the magic is that it worked on a GPU and it worked on a distributed machine, okay? And that is, that is the goal. That is what we're trying to do with many, many, many algorithms, right? We're making a lot of progress. There's more to be done. We need help. We want all of you to help us with this. But this is exactly what we've been doing. So if you want to know what is our secret, how could we do this and other languages couldn't, it's an old idea in science or in computer science, certainly for software. It's abstraction, okay? Abstraction is the key to everything. That in this case, there were 2 uses of abstraction. One is that a data structure could be a mathematical matrix. I used n numbers when n squared, my freshman linear algebra kids would all write out the n by n matrix, if it was 3 by 3 anyway. They'd write out all the numbers first and then proceed. So no, you don't have to get matrix element by element in your data storage. You could work with whatever data storage you have. That's abstraction. But also the architecture is an abstraction, that a matrix itself can be a serial object or a distributed object or a GPU object, right? This is an abstraction too. The human doesn't even want to care in the end of the day am I on a GPU or am I? So the wrong question shouldn't be, how do I program up, do I have to learn CUDA? How do I program GPUs? Those are all the wrong questions for the larger population. The right question is, how do you make it that the large population doesn't need to know CUDA, doesn't need to know MPI? That, I feel, is the true question for parallel computing. And that's what we've been working on. So you could ask, why does Julia let you do this? Well, there are lots of things that that are very useful, and they're all described in this paper. So you can certainly go and look for this paper. But Julia has well-designed abstractions, multiple dispatch, plays nicely with Python, all of these things. I don't have time to go into it in this talk, but it's this combination that we believe has allowed us to solve this hard problem that lots of people have talked about over many, many decades, but arguably have not been able to sort of push too far, into a solution. And again, we don't claim we've solved it, but we think we've built the infrastructure that will allow the world to finally solve this problem. And again, I can't repeat it enough. We're really, really looking for your help in doing this. So that's my demo. I also want to share, as long as I have my browser open, I've got some more slides, but as long as I have my browser open, I just wanted to tell you a little bit about what I've been doing at MIT, because I thought this audience might be interested. We taught a class, and you can see the date on this, April, at MIT. There's my little doggy. That's Philip, the corgi. Dave Sanders did a lot of the lecturing. Philip just sat there and looked cute a lot, but the students appreciated. I don't know, when we went virtual, the students appreciated having a pet nearby. It was some sort of feel-good thing. But anyway, everybody loves dogs. All right. So when in March, at the end of March, or maybe it was middle of March, MIT shut down, and all the students were sent home. And just at that point, it was kind of like the middle of the semester, and kind of on a lark, we decided to turn our computational thinking with Julia class into a class where people write Julia code and they can work on epidemiology, COVID-19. We had some, random balls bumping into each other to simulate, to simulate people infecting each other, right? And then we went to the differential equations, and so there's a whole course online that started on March 30th, and we made all the videos available. And so anybody here is welcome. In fact, I'll tell you what I'll do. I'll put the link here in the chat, so in case you want to look at it right now. Oh, I actually didn't see all of these. I didn't even see all these messages. Oh, it doesn't automatically scroll. Oh, you guys have been talking. That's great. Yes, Julia is just-in-time compiled, and it does use LLVM, which is a technology that certainly helps us move forward very quickly. And so, everybody's answering. This is great. I don't have to say a word. Whoever's doing all these great answers, thank you. John Hearns, thank you for answering. So we have this whole class, and what's great about this class, we believe, and this is our philosophy, is that you learn math while you code it up. So you learn software, and you also, every homework assignment gave something that was related to COVID-19. And so in the first homework, you analyze some data, right? And then you do some probability, and then you do some epidemiology, a simple model, and then a spatial model. And then we ended with some scientific machine learning. And so we went through all these things, and the students loved it. We had, I think there were 300 students signed up at a record speed to take the class. And most of them stuck with it. It was really a fun class. And it's completely done a bit on a lark, but maybe those are the best ways to do things. But that's what we did. All right, let me get back to my slides. I guess I have 4 minutes to my slides, which is fine. Okay, so here I was at the demo. So let me move past the demo. So let me just pick and choose a few more of these slides. I'll go through some of these fast. But yeah, this was the Celeste project mainly at Berkeley, with a little bit of help from MIT and Julia Computing, to do this big machine learning problem, at a petaflop. And again, we don't believe anybody else has ever done that from a high-level language before. So we think that was kind of cool. Let's see, what else do I have? This was the Intel stuff that's coming. But here, let me move ahead a little bit. So I'd like to tell you about the climate modeling, because I'm thinking that's what I'll do at MIT next semester, by the way. More and more students are very interested in the climate. I mean, I think people are starting to accept that COVID-19 will have, we believe there'll be a vaccine, I guess. I don't know, maybe hope that there'll be one within a year or two, and then that'll be it. But global warming and stuff, that's going to be with us a lot longer. And a lot of our younger students are very, very interested in the climate. And so one day last September, I think it was, I was over at MIT, and some of my colleagues over in the Earth and Planetary Science department came over to me and said, we would like to use Julia we're going to throw away our Fortran. Our Fortran is too old, too cruddy. We can't do anything good with it. It took us many, many years, but we're finally getting rid of the Fortran. We're no longer saying we're no longer saying that we can't, we can never rewrite the code. We're now saying we have to rewrite the code. And by the way, we're going to do it in Julia. Don't talk us out of it, but please help us. And so what they did was they said, but we have to check a little bit about performance. We have this little problem. We'd like to give you a couple of weeks, and let's just see if you can get within a factor of 3 of Fortran MPI. And so we took the couple of weeks, and we ran it in Julia, and we got that factor of 3. It was 3 times faster. My students were very proud of themselves for being 3 times faster. So we taught this class. That was before the class I just showed you. This was actually in the fall. The class I just showed you was the spring class. And so, talking about climate change. So that was one thing we did. I guess I have one more minute. Let me say one point, and then I'll go to my concluding slide. I'll have to skip a few slides, but I'll post them if you want to look at them. But it's starting to be the case that code is the math. You don't code the math, code is the math. And that relates to my teaching style, where if you know what these symbols mean, and people in the climate world know exactly what these symbols mean, then you write these up, and then these are the high-level things, and then you can implement them in any way that you like. We like to make the code be the math. There's no more room anymore for, like, when I was a kid, maybe I saw BASIC, I saw alpha, ALPHA, beta, BETA. There's no room for that anymore. And alpha should be the Greek alpha, right? And so forth. All right, I'm going to sort of come to my conclusion. There's so much I'd like to tell you, like opportunities for new algorithms. There's so much I can tell you. But here, let me kind of rush to my concluding slides here by mentioning some of the ideas where Julia's active, where we could certainly use help. Scientific machine learning is what everybody's interested in these days, or maybe that was before COVID-19, I'm not sure. So Julia has become sort of a terrific, leader in scientific machine learning. For those of you who are not speaking this language, machine learning has often been about big data machine learning, where like you feed things a whole lot of apples and a whole lot of oranges, pictures of apples and pictures of oranges. And the human doesn't get involved, and the machine learns what's an apple, what's an orange. But there's a lot of science situations where humans have more knowledge. And so it's sort of more like small data machine learning, but you have some where there are things that humans know, and there are a lot of things humans don't know. And so those are the situations where scientific machine learning comes into its own. And Chris Rackakis, who's in my group, he's an instructor, but he's amazing, is kind of a real leader now in scientific machine learning, and he's just doing amazing things with this that I don't think any other languages are comparing with. So some of you might be interested in that. For the rest of you who are interested in supercomputing, which is the nominal title of this conference, it's all about what I said in the beginning: productivity, portability. From a high-level language, people thought it couldn't be done. I like to say what you want to compute, but not how you want to compute it. And we can actually give even legacy MPI code a new life. So there are a lot of people who are incorporating old MPI code into Julia. It's not exactly our favorite way, but but there are good reasons to do it. And so that also happens. So there it is. Julia is a high-level parallel computing language. We believe that it will solve the great HPC language problem that we've been living with for all these decades. Please participate. I see somebody typed the Julia discourse on the text, so you can. It's a very friendly, as John pointed out. And if you want to participate, feel free to email the lab or just get going on this course. So thank you all very much, and thank you, Marek, for inviting me to give this talk.
Meanwhile, we can start the question and answers. So if anyone has questions, please write them in the chat.
Somebody wrote he loves linear algebra. That's nice to know. And then I see the icon. Okay.
Someone asked if ICM is using Julia. That's interesting. Some people are using it. We have now a computational engineering course where one of our instructors is teaching Julia. So that's our first attempt to teach Julia at the University of Warsaw at ICM. But we know that there's a very strong group in Warsaw. Yes, Alan. I'm sorry, I don't want to.
I was going to say that people ask, a version of that question everywhere I go. Like sometimes I even go inside private companies, and I'll be talking to the CTO, and they'll ask me, hey, is anybody, I don't know if anybody in my organization is using Julia. And then I actually go and look it up, and I find out that, like, at the grassroots, like, oh yes, there's this group in your organization. There's a dozen people using Julia, and you don't even know about it, right? Because Julia is like that. It is very much a grassroots kind of thing. So there are usually lots of young people are using it, and again, sometimes you wouldn't even know about it. So another question was about Julia and quantum computing, and there's a whole group. I'm not the expert on that one, but there's tons of stuff that are happening in that area. I keep thinking that I really ought to get involved with that. But here, let me go ahead and share my screen again and just show you something. So am I able? Oh, yeah, there you go. So differentiable quantum programming is sort of one big exciting thing. And so let me just kind of briefly tell you about the idea of differentiable programming, because that's another concept that Julia is particularly terrific about. And so some of you might have heard about automatic differentiation. It shows up in machine learning. The idea is that programs should be able to, you should be able to find the derivative of not a formula like when you learn calculus, but you should be able to differentiate, a program, which literally means that a program is, in some sense, is building up formulas upon formulas, right? It's doing math, and therefore you should be able to differentiate it. And by the way, even though your calculus teacher would tell you when things are not continuous, you can't differentiate, since everything on a computer is almost always sort of piecewise differentiable, sort of maybe, that I won't explain that, but maybe you'll believe me. It should be possible for not only to differentiate programs, but you have to differentiate programs that call other programs. So one of the problems, for example, of calling LAPACK, which is great for just doing linear algebra, is you can't differentiate through it. So of course you could teach your software the derivative, and that's what people are doing now. You could teach the libraries the derivative, but what people want more and more is just that you can differentiate all the way through. And so that is what this YAO program is doing. So that you could look into this. I don't know much about it, but I hear people talking about it. Let me go to the next question. A hands-on session. I'd be happy to do that. You can convince Marek to invite me.
Yes, sure. People will comment on that. I will comment on that later.
Okay, I'm perfectly happy to do that. I mean, I do this all the time. Yeah, glad to hear people are. But of course, you could go to our MIT lectures, and you might start being able to learn from that. There are other lectures online. There's, let me see if I could find this one. There's, what's her name? Huda Julia Academy. There's this thing going on. Huda Nasser has been doing these incredibly great beginning classes. There she, data science. These two on the Julia Academy are things I think they're free. I think I'm actually not sure. Let me not say because I'm not sure. But yeah, I forget what the story is. But these are two other ways to learn. Oh, even our MIT class was brought into that. I see they grabbed it. And there's other, if you go to julialang.org, I mean, some people like to learn from books, some people like to learn by doing. But if you go to julialang.org and you look at Learn, there's just lots of stuff, and you just got to pick your favorite. I'm a big fan of anything that David Sanders does. So there's various things out there. This one's in Spanish. Take your pick of what you'd want to use, but get in there, and like anything else, your first 3 days of learning Julia, you're going to curse the fact that we use square brackets or we're one-based or whatever. Some people like zero-based languages, but after you get through those first 3 days, you're going to start to see some of the cool things you can be doing with Julia. Differential geometry by V.I. Arnold. You're kidding me? That could be fun. So is Julia replacing DSL approaches? So the answer to that question is people, I don't know, I wouldn't use the word replace. People are building DSLs left and right in Julia. So the most popular one is probably JUMP. So I'll just kind of go over and show it to you. So in optimization, so this is an optimization language, and it's Julia for mathematical programming. That's what JUMP stands for. And it's gotten incredibly popular, particularly in the economics community and believe it or not, in the business schools. People are using JUMP a lot. Like, who would have thought? So JUMP is a DSL for optimization. There are other DSLs that are being built in Julia. And so that gets into sort of fancy Julia programming, but Julia is a particularly good language for implementing languages because of the various abstractions that I pointed out. So that's, I guess, all I'll say about that. Will Julia-based deep learning frameworks like Flux outperform PyTorch and TensorFlow? So the answer to that is I don't think so. So here's my story about PyTorch and TensorFlow. Anytime you have something that's been optimized for a particular purpose, like machine learning, with lots of resources going into it, then I wouldn't expect to be able to compete with that. Like, who would, right? I mean, especially these packages have had a lot of users, banging on those things, doing a lot of performance engineering and so forth. But suppose this is where Julia comes in. So if you're doing what PyTorch or TensorFlow does, fine, go ahead and use it. I mean, we're not going to compete with that. If, however, you want to start moving away from exactly what that does, that is where Julia shines, right? When you want to do what everybody else is doing, go for it. Just use it. Don't use Julia for that. You want to be, an innovator and do something that nobody else is doing, especially like scientific machine learning, then that's where I would recommend using Julia. Okay. Okay. What if one heavily depends on specialized stencils? Okay. Lots and lots of people want specialized stencils for boundary conditions, matrix-free Krylov methods. By the way, my picture is very little, and Marek's picture is big, which is fine.
We should change. Okay, I think I will just switch.
Oh, okay. I think it's because you were on, but only because I'm making hand gestures. I don't know if they're useful or not for communicating. Otherwise, I like looking at you, Marek. Don't get me wrong. Yeah. So I think we need to build up our stencil library. I'm not quite sure what the status of it is, but I would encourage. I would actually tell you to email. If you've got some stencils, you're not the only one. Email the JuliaLab at the address I mentioned. Valentin will see it, and if you know, if enough people see it, maybe we'll build it, or if we get funding to build it, we'll build it. But we really need, I mean, we probably have halfway decent stencils, but I think we can do better. So, and I want to see that happen. You know, building a good stencil library requires some work, but it would be worth it to do it in Julia. You see, if we do it in Julia, then you could differentiate through it, or, you know, or you could pass it through different kinds of architectures. And so, you know, having that abstraction would be fantastic. Right now, though, there is something I will mention for people wanting to do stencils, just in case you think that there's nothing at all. There is, maybe I can go back to my presentation. I'll just mention one thing. So when I go to my presentation, at the moment I see Marek's presentation. Now I see mine. All right, let me see if I can just pick out a slide that I had, if I could find it quickly. I may not find it quickly. If I don't find it quickly, I'll just type it. You know what? Let me actually do it the other way. Let me go to my browser and mention kernel abstractions.jl. So for people who want to get things going on GPUs quickly, do some heterogeneous computing, maybe even stencils, this is the package you want to go to, kernel abstractions.jl. And if it doesn't do what you want, email the main developer of this is Valentin, and I would just encourage you to go ahead and let's see if Valentin's still the main person. There he is. Vicharavi is his handle. Just go ahead and tell him this is what you want, and we'll see what we can do for you. All right, let's see. What other questions? Yep. So can we do machine learning in Julia? That's what flux.jl is all about. So I kind of answered that a little bit, but maybe I started in the middle. So let me go back to the beginning. So flux.jl is basically our PyTorch or TensorFlow. And it's completely, it's Julia. So here it is. It's 100% pure Julia from beginning to end. So if you actually look at PyTorch, a lot of people think PyTorch was written in Python. I forgot what the exact number was, but I think it was like 30% Python and a lot of C and some other things. So PyTorch is definitely not implemented in Python. It's just callable from Python. All of Julia is callable from Python too. So I mean, callable from Python is not really a feature. Anybody can do that. But the fact that it's all 100% Julia means that you get the composability of different libraries, which you wouldn't get through PyTorch. Okay, did I get to all the questions? Let's see. Let me just go back to see if I haven't missed anything. The loving usage for GPU, that's great. Is Julia, I think I answered that one. Model vector fields. I'm well in favor of Julia for all kinds of mathematics. Yeah, I would absolutely encourage people to just get in there, start contributing, start writing things. At first, people write things the way they write in another language. Then Julia will coax you to get to be a better Julia user. In fact, anytime you want, you can actually see all the Julia code, and so you can see how the fancy people do it. So nothing is hidden in Julia. I mean, you might say Python is open source, and it is. But if you ever look at a Python code, right away you tend to see C code, right? And and that is okay if you're a C programmer, but in any event, you're forced to move outside of your comfort language, right? If you're a Python programmer, you want to stay within Python. Julia, much of the time, I mean, of course, we do call libraries like LAPACK, but much of the time, Julia code is written in Julia, right? All the way down to LLVM eventually. But much of Julia is written in Julia, and so you don't have to leave your paradigm if you want to see how things are implemented at the lower level. When do I expect Julia to catch up with Python in terms of number of packages and usage in academia industry? Well, I don't know. Python had what, a 30-year head start? But we're catching up? I don't know. I think that I don't worry about, I'm very happy for Julia and Python to coexist. I don't know when will Python Julia catch up. I just remember when, believe it or not, there was a time, I think the year was around 2000, when I recommended that maybe some people start using Python. And everybody shot me down and saying, no, nobody wants to use that language. Nobody's using that. So the funny thing about languages is it often goes from nobody's using it to everybody's using it in a very discontinuous way. So I don't worry about those things. Yeah, so at MIT, we do most of our things in pure Julia. That's the next question. Are there connectors to R and Python? Absolutely. So, and in fact, we in Julia, we actually sometimes run Python libraries, and Python people run Julia libraries. It's completely interchangeable. I don't know so much about R, but I think you could do the same, but maybe not as easily. I'm not sure. But certainly Python, the interconnectivity between Python and Julia is very, very, very strong. Are people using the STAN interface? I hear they are, but I hear that the thing that is growing. So STAN is the statistics package that was originally authored by my good friend Andrew Gelman. Andrew Gelman and I were postdocs together. We used to actually swim together and play frisbee together a long, long time ago. And I think Andrew told me that he started doing STAN when he saw the success of Julia. But he wasn't using Julia at the time. But there's another package. Oh, what is the name? There's another package that's kind of similar to STAN, and I'm blanking on the name right now. That does that sort of probabilistic inference in Julia. Turing, that's the one. I should remember that. Turing.jl, I hear, is giving STAN a bit of a run for the money. So even though Andrew's a good friend of mine, you might want to consider Turing.jl. So if you're a STAN user, of course, if you just want to call STAN from JL, STAN, there is a STAN. If you really like STAN, which is fine. You can call. The difference is here you're calling the STAN package, which you may already know and love. But if you want to actually do it the Julia way, that's where I would recommend moving towards Turing. So it's your choice. I wouldn't want to tell you what to do. So already I see people answered me. Thank you. Which is the recommended IDE for Julia? I don't know. A lot of people like Atom. Others like VS Code. I don't know what's the best IDE. This is the sort of thing, take your pick. People are here voting with Adam. An ARC call for R integration. What is it? Can you still get away with Vim? You could get away with anything. People do. So that's a good question. A high-level framework for writing regression tests for HPC systems. I feel we need this. I don't quite know what we have right now, but I think that would be a really good thing to have. I mean, and I myself, we have somebody in the JuliaLab who I'm hoping very soon will start building this sort of thing, because this is what I'd like to see myself. Okay, other people like Adam Juno, that's cool. All right, I think I've quickly admitted. How much time can we go to, by the way, or what's the usual ending time? Wasn't quite sure. I mean, I could stay on another 10 minutes or so. But
as long as there's still interest, and people are free to leave, and
okay.
free to stay. So it's as long as we have, I would make a sort of. We don't have to release the route for the next speaker, Alan. That's a good part.
I understand the talk is recorded, right, Marek? I've seen that.
Yes, of course. Sure.
And it'll go on the web, free for anyone to watch, right?
Yes, of course.
I don't understand the question about second language programming. What does that mean? I guess I don't understand what second language programming means. Is that a term? John, thank you for that answer about regression tests. Yeah, I just don't understand the question. There's this question by Patricio. But it is true that Python and R are mainly implemented in C, while Julia is mainly implemented in Julia, and that is that is, yeah, Julia uses C libraries, uses other libraries as well. Even there's a little bit of Lisp in Julia too, believe it or not, down at the bottom. But it really is a different kind of animal in that, when I was growing up, people said to me that a language could either be fast, but then it'll be a little harder to use, or if it's easier on the human, then it's necessarily slower because like it'll probably be interpreted or something. And people made it like it was a law of physics that it could be one or the other, and it couldn't be both. And I guess we set out on the Julia project because we didn't believe that it was a law of physics. We believed it was a happenstance to date that interpreted languages were slow and compiled languages were fast. I thought that was sort of the evidence on the ground, but not a scientific law of nature. And so we wanted to show that with just-in-time compiling, you could basically have a dynamic language and still be just as fast as C. So I don't know if that was the question that was asked, but I decided to answer it that way. Where does the name Julia come from? That question comes up all the time. And it's the best question, and it's got the lousiest answer, I'm sorry to say. So Julia was named by Jeff Bezanson, one of the four folks in the picture I showed you. And Jeff actually had a couple of Julias before this Julia. So Jeff always wanted to create a popular programming language ever since he was, I don't know, I'll say ever since he was in college, but I think it was ever since he was 5 years old. He wanted to write a programming language. And so when he was at Harvard as an undergrad, and I gather he was like talking to, I gather there was a programming language mafia at Harvard when he was an undergrad. A couple of these guys were talking about creating a language, and they talked about what to name it. And somebody said, you can name it anything. Name it Julia. Who cares? And so that's the name, even though the first couple of Julias were not the language that we know today. So I'm sorry to say that Julia is not anybody's wife or girlfriend or niece, and it's not named after the mathematician Julia. But it is a good name. I mean, like at the very least, we didn't name our language after a snake. I mean, come on, right? And it's not, so it is a good name, and we can. I mean, I could try to Google Julia right now. I mean, Julia Roberts is long since used to be on top, but I think we're on top now. This is my machine. Maybe you could try your own, but Julia Roberts is nowhere to be found on my computer anymore. But Julia Roberts used to be on top. So that's the best answer I can tell you. Sorry, I don't have a better answer. But it is a good name. I mean, we're not the first language to be named after a human or even after a woman. There was Ada, and there was Linda, and there was one or two languages named after men. I forgot. Maybe some of you could think of it, but there have been a few. Stan, I guess, if you want to count Stan as a language, his name, that's a male name. So yeah, so there's certainly a tradition of naming languages after human names. Romeo and Julia, okay. Which is your utopic view about Julia in the future? I mean, what can I say? I mean, I think you've heard my view. I would like to see the problem of I mean, there's a lot I can say about my view about Julia, my view about computing, my view about algorithms. They're all intertwined. That's why I'm a little bit flustered by the question. But my view is that people should be able to, I mean, I guess there's something my advisor used to say, and maybe he still says. When I was a graduate student, my PhD thesis advisor was Nick Trefethen, who's been at Oxford lately. So he used to talk about computation at the speed of thought. And by that, he meant that if you could think something, you should be able to compute it, right? Nothing should stand in your way, right? You want to try out a computational idea, you should just be able to do it the moment you could think of it, right? So, you wake up in the morning, you take a shower, you think of a computation you want to do. You want to be able to do that right away, instantly, without any friction. So I guess that's my utopian view. Whether it's on it doesn't matter what kind of machine you have, whatever machine you can get your hands on, but you should be able to do it quickly. because if you could do it quickly, then you can get to the next step, and you can interact with it, and you can, you can sort of do mathematics in a way, computation in a way that we've all dreamed of. That would be my utopian view. Yeah. Read my minds. Yeah. Okay. Is that a question about stream benchmarks? I have no idea, but Valentin might know. So I also have no idea about mutable arithmetic in Julia. Again, I would Google just like you. Nobody in my group is working on that. But what is this? Mutable arithmetics.jl. Is there anything good here? I mean, this is not my group, so I wouldn't even know. So yeah, I'm probably the wrong person to answer that one. So all right, so the open BLOS thing is very much still under development, and there is one person in my group who is working on that, and that is Yingbo. So that's where I would absolutely, if people want more of that, I would absolutely, bug Yingbo and see if we can make that happen. But he's in my group, so and he's the one who's kind of working a lot on this these days. But he's also working on other things. Julia does work on Raspberry Pis. There's a great demo of that, and there was I think there was an elementary school student who won a prize at one of the Julia cons. Let me see if I can find it. Raspberry Pi Julia something. So yeah, people play with this. It's kind of fun. But so yeah, so you can look at this. There it is. So here's Minecraft. So I think it was yeah, let me just see. Yeah, go ahead. Give it a try. So apparently it works. So Avik's son actually was the person who was doing this. So you can play with this. I think Avik was giving the talk, but at one point Avik's son was present at the JuliaCon and talked about it. So yeah, so definitely you can do Raspberry Pi. Yep, we're still working on SIMD SIPR. Always improving. Julia gets better every day. What can I say? But there's always more and more stuff coming, and there's always more stuff to do. That's why we need all you guys to get. We need applications. We need people getting down into the guts. We need all of you to get on there and start making this happen. There's lots of work to be done. But the moment you do something, you get the multiplier. You do something, and then thousands of people will immediately. I'll tell you what's really fun. When you do something because you wanted it, and another person uses it in a way, in a package that you never expected. Like, I'll give you a crazy example. One person writes interval arithmetic. For whatever reason, if you know what interval arithmetic it is, it's a way of like bounding your computation from below and above. So you write interval arithmetic just for a CPU, and then somebody else comes along and writes some GPU code, and boom, it works together. Someone else comes along and writes an eigenvalue algorithm. Well, look at that. You can have your eigenvalue algorithm on a GPU and running an interval arithmetic. That kind of crazy composability is something that I love. I love the stories. If it happens to you, I want you to tell me, because I love crazy composability. It's just the best. So could Julia be used for system programming, as opposed to what? As opposed to C or Python? I mean, so people, I'm not a system programmer. Again, I'm not the right person to answer that probably. But what people say is, people want a typecast. They want like R to be the statistics language, right? And and Python maybe is sort of the computer science language, but Julia really is a general purpose language, and what people do with it is up to them. So can you use it for system programming? I don't know, but it is certainly not meant to be typecast as any one kind of language. So it's got elements of system programming and elements of mathematics. It's kind of been a mixture of lots and lots of things. I think I only have one more minute because I have believe it or not, I have a meeting I have to go to online in a couple of minutes.
Right. There was someone typing. I can see.
No, I think the questions have converged.
Yes. So, thank you very much, Alan. That was great. Really, really fantastic. And I can see there's lots of interest. There was question whether we will have any hands-on or sessions for Julia. And I may say, if you are really interested, please write to us, ICM. And after maybe next 3-4 lectures of seminar series, we'll take a little bit of break for July, August perhaps, but during that time, we might run summer schools or summer workshops or things like that in a different format, more hands-on. And if you like Julia, you would like to learn Julia and so on style, we have experts in Warsaw. I will be talking to them, and we can ask Alan to help us with this with his students, and we can run it. So maybe in July, August, if there is interest, I'll be of course very open to that suggestion.
All right. Well, great. Well, thanks, Mark, and thanks everybody. This was fun.